and welcome to E2E Network's webinar on practical large language models using LLMs in your business with Python with Jonathan Milvus. I'm Uzma, and I'll be your host for today. Let me now take a moment to introduce you to our speaker for today, Dr. Jonathan Milvus. Jonathan, a distinguished figure in the field of artificial intelligence and machine learning, earned his PhD from the University of Texas, where his research focused on developmental robotics. Following his doctoral studies, Dr. Mugen held a prestigious postdoctoral position at Carnegie Mellon University, where he contributed significantly to the intersection of machine learning and human-computer interaction. Notably, his work addressed the critical issue of user privacy preferences in modern devices. In addition to his scholarly pursuits, he is also a respected author, with his book The Curiosity Cycle, Preparing Your Child for the Ongoing Technological Explosion, gaining widespread acclaim. Now, on to the main event. Jonathan, thank you for being here. Over to you now.
Okay, hello. So let me see if I can share my screen here. There it is. And desktop one. Now, if we're really lucky, it'll let me put it in presentation mode. Okay. So there we are. So let's see. And get this thing out of the way. I guess imagine you guys can't see that. All right. So here we are. So there's a lot of links in this talk, and so you can go to my website, jonathanmugen.com, writing and press. There's not really press. I don't know why I say press, but if you go there, I originally gave this talk in person in Austin at a paid event. Well, you had to pay to go. I didn't get any money, but you had to pay to go. But this is the first time it's ever been given online, so everybody can see it. So, but the slides are here, and there's a lot of links, so so you can go and learn more and follow up. So you can just go there. And so here we are. And it is really annoying that this thing is right in the middle of my talk here. This little screen, so I can't even see what I'm looking at. But okay, hopefully it'll go away. Dock to top. All right, well, that helps a little bit. Okay, so ChatGPT can teach us the nature of the universe. I had a conversation with it about general relativity and how space and time were similar or in the same thing. It's not space and time, it's space-time. They're all together. And then when we fall, we're actually moving towards a large mass in space-time. It's not that we're being pulled by some force. We're actually moving through space and time towards this mass. And this was amazing that it was able to have this conversation with me and help me get over some of these conceptual hurdles. Now, of course, I still don't understand space-time or general relativity or any of that, but I have a much better understanding than I did before. And so let's talk about something important, though. This is how can you do flexible search on your documents? And I really like doing all the science stuff, but we actually have to get things done in the real world. So here we are. So flexible search over your documents. So what we're going to do is we're going to talk about how you can use LLMs in your business or at your work or on your personal projects using your own data to do cool stuff, not just talk about the nature of the universe. And so the first thing will be how you can flexibly search your documents better than before with keyword search, and then how we can move to question answering over documents. So we can actually then involve the LLM and have the LLM use your information when it's answering questions. And then we'll talk about how the LLM can do exact calculations. So how it can do exact calculations. And But then we'll talk about some considerations when using LLMs. There's some things you need to keep in mind. And then finally, we'll go into a little bit of detail about how LLMs work at the matrix multiplication level. And that should help you understand some of the considerations when using LLMs. So flexible search over your documents. So flexible search uses vectors, which is long sequences of numbers to represent concepts in text. So because as Led Zeppelin taught us, words can have more than one meaning. So imagine you search for fans. So if you search for fans, these kinds of fans may come up. But imagine that you're actually interested in people who follow a particular sport. You're interested in that kind of fan. Well, then keywords are kind of stuck. And imagine you want to search for sports fans, but you're really interested in your local sports team, maybe in Milwaukee, in the United States, it might be the Milwaukee Brewers. And so if you search sports fans Milwaukee, it would still pull up the Brewers, the local team, because of vector searches look at things similar. So what they do, this is like called semantic search. So you're trained on, these algorithms are trained by taking your embedding. So you say sports fans Milwaukee, and sentences that are similar to that are pushed in embedding space, where the embedding is where the vectors stay in high dimensional space. We all remember from high school, X and Y, and you can plot things in space, but of course in vectors, these are like 1,000-dimensional space, and you can push things closer together and move things further apart that are not similar. And these algorithms are trained to do that. So then when you type in something such as sports fans, the embedding of fans of a particular team or the name of the team is actually fairly close in embedding space. And that's called semantic search. So there are multiple steps to do semantic search. So the first step, of course, is you gather your documents. And here's all the links I was talking about. So if you just go to the main site, you can get all these. But what you do to do this sort of semantic search is you break your documents into chunks, because it's hard to embed a whole document to get one vector, even if it's 1,000 long, that really represents all of the different ideas in the document. So you break it up into chunks like of paragraphs, and you break it up into chunks. And then and there are tools to do this, such as Llama Index and LangChain. And then for each chunk, you embed it, which means you convert it into a vector. And so you can use sentence transformers. OpenAI has an embedding service, or you can download TensorFlow Universal Sentence Encoder. Actually works pretty well. And so you can embed the chunks, and then you put the chunks in a vector DB, and a vector DB stores each vector. So then when you have some question later about sports fans, you can find the similar one. So the vector database stores everything and allows you to do a search really fast. And often there's an algorithm associated with that. So you don't have to do a linear search where look at each vector and compare to distance, and the next vector compare to distance, next vector compare to distance. And that's it. So now there's a question. I'm not sure quite how we're handling questions. Let's see. Can you please go to the first slide? Oh, yes, I can. Let's do that. And so you can see the link again. In fact, I bet I can put it in the chat, the link. No, I can't. It won't let me select here. So it's www.jonathanmugen.com. And then if you go to from there, it's easy. There's navigation, but you can go to Writing and Press, and then it'll be this talk, but this talk that as it was originally given in Austin, this is a slightly edited and updated version of that. Type your answer. Let's see, I can do that. www.jonathanmugen.com, Writing and Press. There we are. Okay, great. So now we're back. Here we go. All right, now, cool. Thank you for that question. Now we got that. So then you put things in a vector database, and there's many vector databases out there. There's Pinecone is probably one of the most familiar. It's an online service. Milvus, you can have an online service, or you can download and run it yourself in Docker. That's usually what I use. But you can also use Azure AI Search, which was formerly Cognitive Search. And then you can do you can also just store it in memory if it's small enough. And then from Facebook is the way so you can quickly look through and find your things you need. And then you can also use like scikit-learn k-nearest neighbor. Okay, so here is the process and how it looks. So you've got some user, and the user makes a query to the embedder, and the embedder, you know, if you want to say, I want to find sports fans in Dallas, Texas, and then that gets the embedder converts it into a vector. Then that vector then goes into the vector database, and it looks in the vector database for similar vectors. And that would be the chunks, the vectors of the chunks that you embedded. Remember, for every document, we broke it into chunks, say like at paragraph level, and it would find the relevant paragraphs that are close in embedding space, and it would pass those back to you. And that's the semantic search process. So you can also then re-rank them at the end with LLMs or do hybrid search, and we'll see that in a moment. So that's the semantic search, and that's the most basic. And this was a pretty big advance, say in 10 years ago. But now we're starting to use LLMs. You can not only do easy semantic search over your documents, but you can actually talk to your documents, your own documents, not just about the nature of the universe, but your own documents. And so, and this is the process here. It's the same process, the initial process of loading your documents into the vector database. But then here is the sequence diagram. So the user then asks a question, it goes to the embedder, and then the question as a vector goes to the vector database, just as before, but instead of the answer coming directly back, the question plus the relevant chunks, the relevant pieces of your document, go to the large language model in the form of a prompt. So the prompt in a large language model is where you just basically, if you're using ChatGPT online, it's just where you ask it the question. And then, of course, in the background, they have an additional prompt. But basically, it's where you ask it the question. But when you're using the LLM, like in an API mode, you give it the whole prompt, and you'll say, you are a helpful large language model helping me answer questions on my document. Please return the answers given the relevant documentation below. And then you paste in the documentation, and then that whole thing goes to the LLM, and the answer comes back. Oh, and we have a question. Let's see. And then the question is, how do we assess the upper limit on the number of PDFs that can be fed? There really isn't an upper limit. So let's see, if I do answer live, what does that do? You would like to answer this question. Done. Okay, so there really isn't an upper limit on the number of documents. So if we go back here, when you put the documents into vector DB, what you're doing is allowing them to be searched non-linearly. So you're using fancy algorithms to quickly find the chunk you're looking for. So which means that vector DB can grow to an unbounded size. I mean, it's not unbounded. I imagine there's atoms in the universe and all that kind of stuff. But the vector DB can be really big. So it's not a problem of how big your database is. And that's in contrast to when you have a prompt and you send everything to the LLM, there's that context limit that you hear about. And of course, the context limit was just recently raised by Microsoft. No, wasn't Google. Sorry, they came out with the new context limit. But here, that's the idea: is you're getting around this context limit by going into the vector database and grabbing only the pieces that are relevant to your question, and then you send just those relevant pieces to the large language model. And then the great thing is you can ask questions, and then you can follow up. So when you get the answer back, you can ask additional follow-up questions, and those get embedded in the vector database. And then you find the vector, and then you send the whole previous conversation, your follow-up question, and then the relevant documentation to the LLM. So you have to manage memory yourself. The LLM doesn't have memory. And so then the answer comes back, and then you keep doing that. And every time you ask a follow-up question, behind the scenes, you have to add the prompt. You keep a whole prompt of what's been said, and you have to add your additional question at the end, and then the LLM reads the whole prompt anew. And that's where the prompt limit, another place where the prompt limit comes in, is if the conversation gets really long, then you need to like summarize it. And there are tools within LangChain to do that and to handle that. But this is that process. And then this is called retrieval augmented generation, or RAG. And so it allows you to get around that prompt limit of how long your prompt can be by going into the vector database and pulling out the relevant pieces of your data and sending them across. Okay, so now some notes on this. The LLM, of course, is trained on the whole internet, more or less, and it will always answer. So if you ask it a question about something that's outside of your documentation, it'll still usually give an answer. You can put in a prompt, hey, don't answer the question if it's not in the documentation that I send to you, and it'll sometimes respect that, but not always. And as we talked about, you must manage your history, and then here's another link you can follow up. So you can use software frameworks to help manage this process. But if you do that, you have to pull together all of these different abstractions that they've built on top of the core API of whatever LLM you're using. And I think it's worth it. But a lot of people have complained about how these abstractions are not the ones they would write if they were writing the abstractions. And it is a pain to learn the abstractions, but and often you have to go actually into the code, either of LangChain or Llama Index, and figure out what exactly is happening with these abstractions. But it's probably worth it. Or you can use even this LangChain Llama Index, or you can use even a bigger set of abstractions and go ahead and use something like Azure Cognitive Search, which has a lot of this stuff built into it. And I wanted to point out hybrid search, which I mentioned earlier. So you can imagine you're looking for like a part number or something of some sort of machine, and it's part number 568Q48. You wouldn't necessarily want to use a vector representation of that. You want keyword search. And so Azure has a nice way you can integrate vector search and keyword search together in hybrid search. So here's if you're already in Azure shop, I would probably start here if you want to maintain flexibility to go between different things, then you can use the Llama Index. In fact, this is yeah. And so the sponsor of this talk is actually a cloud computing. So they may have different opinions on that. But here we are. So here's the open things that you can use on any Llama Index and LangChain. You can use on any set of cloud. And then this is a particular provider that I have some experience with. Okay. And so then the next thing is what we've seen so far is getting particular words of output. But sometimes you want structured output because the output is not going to be read by a human, but maybe another machine down the line. And so you want something like JSON, right? And so ChatGPT, you can do that through the API. So you can specify, hey, I want JSON. You can tell you can tell a large language model in the prompt, hey, return JSON, and it will often return JSON. It'll often ignore you, or it'll often say something in the response, oh yeah, here's the JSON, and then followed by some JSON. But of course, if you're trying to send this data directly to another computer downstream, that initial part of that, oh, here's the JSON, will screw it up because it's not all JSON. And there's a bunch of jokes online about getting it to return JSON. So one thing you could do, yeah, one thing that actually worked is someone said, if you don't return JSON, people will die. And then it finally returned JSON, which is kind of funny. It's like, okay, people will die. But what you can do is you can get around that by making a function call. So OpenAI added something called function calls. And so it kind of looks like this, kind of convoluted. And you say, okay, I'm defining this function. The name is get current weather, and the parameters are location for where to get the weather, which is a string, and whether you want Celsius or Fahrenheit. Fahrenheit, that Fahrenheit, that weird thing that Americans use. And so if you do this, and you can say, okay, but don't actually call the function, just return the arguments. It's based in the, when you make the call, then it will give you JSON, which is, and you don't even need to call the function, but this is just JSON of the form 2 strings. And that works pretty well. I've used that process. So I just make up a function that would take this JSON, and then it'll return JSON because it's part of the API process. Now, you can also, within LangChain and Llama Index, they have output parsers, which are supposed to return JSON, but these don't fully get around the problem. When I looked into the code, it was something like adding to the prompt, telling the OpenAI to return, or whatever language model you're using, to return JSON. And which is kind of funny. You can just do that yourself. But they have some other things that'll be helpful. So you could look at these and see if they suit your needs, but they're not mandating that the language model return JSON. They're just asking. Last I checked. You can mandate that the language model return JSON if you're running your own language model. So if you have access to the actual probabilities of the output for each additional word, and we'll see this in more detail later, but the way they work is they generate one word at a time in the response. If you have the probabilities over all the words they could have generated, you can clamp it down and say, if that next word is invalid JSON, don't generate it. So if I'm looking for a closed parentheses or a closed curly, and if it's not a closed curly, don't generate it. You can clamp it down, but you have to have actual access to the LLM to do that. So there's guidance from Microsoft, and LMQL are 2 prominent libraries for that. Okay, so now that's, we talked about searching your documents, and we talked about conversation with your documents, and we did a little bit on getting structured information from your documents in the form of JSON. But can we take it a step further and do exact calculations? And it turns out we kind of can, right? So in fact, we're getting to the point where I'm not a superhero person, but my family loves superhero movies, so I've seen them all. And there's a scene in Avengers Endgame where Tony Stark works out time travel by having a conversation with a machine. And we're actually getting that pretty far. And then I asked ChatGPT to generate a picture of that, and it gave me something that looked a little bit more like Doctor Strange, but that's okay, still pretty cool. So let's look at an interesting example here. So there was a paper by Google not too long ago that they had this system, and they found that the more the doctor relied on their own intuition versus using the system, the worse the doctor did. And so, let me stop and answer a question. So how can we distinguish between play a Michael Jackson horror song and play a Michael Jackson world song from the 90s? Would JSON help? What kind of data would be able to do this? So yes, the question is, if you wanted to get the Michael Jackson horror song would be Thriller, probably, and the Michael Jackson world song would be from the 90s, maybe something like We Are the World, where he was involved. So the vectors are actually pretty good at this. So if you put in Michael Jackson scary song, it's going to find it, most likely. Or if you do Michael Jackson world song, it's going to find it. The vectors are really good for this, and that's a great example, like horror versus scary. The vectors would be very close in embedding space, and and then world song, it would know We Are the World and Save the Children, and all that would be close in embedding space, and it should be able to find it. So this is a great example of where embeddings work really well. So and then this is the model underneath it, how that works, I'll show in the last section. Cool. So yes, and so this funny thing that happened here, and this is, well, it's not funny, it's interesting. So the more the doctor relied on their own brain, the worse they did in coming up with diagnoses. Now these are hard cases, and you can see they might be, you can see why this might be, because doctor's going to use their own experience, and if it's something outside of that experience, you can see why using some other set of information, such as their tool, or just Google search, would help. So, but now what I wanted to do is, in this paper they had a nice diagram, but I wanted to change it a little bit to show you this diagram instead, because I thought it was more informative. But I wanted to generate this bar chart. And so anyone with experience with Python knows plotting in Python is a real pain. There's like one library, matplotlib, and it has two interfaces, and it's really confusing. And so it's really nice to have some help with that. So if you look here, here's the conversation I had. So I said, draw me a bar chart with these values. And it plotted it. I was like, okay, that's pretty good. But then I had that conversation. Remember, we talked about you can have a conversation. I said, okay, make the x-axis, AMIE only. I'm sorry, the y-axis, and then make the bars these particular values. And it said, okay, and it generated the chart. It was pretty cool. And it does this really well. And then what it's doing is it's actually generating Python code that it runs itself and shows you the result. But you can ask for the code itself, and you can do this through the API or the all language models. Most language models can do this. And so here's the code itself. So what we have here is, through a conversation, it generated Python code that could be then run on some other system. And so it actually generated Python code that gave an answer, which gives us a little bit to this Tony Stark thing, where Tony Stark asked about, in the movie, asked about the eigenvalues of something or other. And then when the system ran it through, the system actually generated code. Well, it didn't tell us how it worked underneath, but you can imagine underneath it created some code, ran it, and gave a result that actually gave the result for time travel. And so this is kind of getting to that process, which is really amazing. And so this is like an example of tool use, where the Python interpreter itself is a tool. Another tool is SQL in a relational database. So imagine you have a relational database and you want answers from that. Here is the process. So it builds on what we've seen before. So you ask your question gets embedded. You pull out the vector database for the relevant documentation. And in this time, in the vector database, there's also the database schema. So when you're pulling out the vector database, you're actually grabbing the schema requirements, which is something like the schema requirements. So it could be, give me the relevant tables. And in your database schema, you then pull out the relevant tables, and then for each table in that schema has the list of fields, and each field has a description in text with it, if you have good documentation in your database. And then what you do is you can pass that to a PHI scraper, which is if you can optionally, if you don't want to send your data to the cloud, you can send it to a scraper that will pull out replace names. We'll go into a little bit in this in a moment. But so the main point here is that you have to send to the LLM, you send your question and the relevant parts of your database, just the schema, so the names of the tables and the names of the fields with some descriptions of the fields if you have them, and you send that to the LLM. So that goes across the LLM, and the LLM returns SQL, just like it returned Python before. And then you can execute that SQL on your own database. So your database is running on your system. You execute the SQL, and then you return that whole thing back to the user. So that's a pretty powerful chain. Now, it's a long chain, and the biggest place where it can break down is if it returns SQL that isn't quite right. If you have a hugely complex database, then it can be hard to send it just the right pieces so it can return the right SQL and have it work. But it works surprisingly well. So that's pretty cool. And then it doesn't need to be SQL. It could be like if you have MongoDB, it could be that language. But you might need, if you're not using SQL, you might need to give it some examples in the prompt of what you want. But this is a pretty powerful process. And so we've seen how to search, like with the Michael Jackson or the fans example, using vectors, right? And we've seen how to pass your own information to the documents, and we've seen how to do autonomous calculations. So now let's look at some considerations when using LLMs. So the biggest problem is hallucination. It'll just make up answers every now and then. So if you have a user-facing thing and it's interfacing with your system and the user is asking your system questions, it can just make stuff up. So there was an example recently with, I think it was like Canadian Airlines, and their LLM made up that they had a refund policy that they didn't have. And it told the customer, yeah, you can get a refund, but that wasn't their policy. And then the court mandated that they actually had to honor that refund that the LLM just hallucinated. So that is a challenge. I think it's worth working around, and it doesn't mean you shouldn't use them, but just know that it's a problem that you have to deal with. Some people call it confabulation instead of hallucination. That's maybe more accurate, but I don't see why people get so caught up in things like that. But confabulation is another word to think of. It's just making stuff up. So it's best if there's some way that the answers can be checked. So we remember from high school, when you do algebra to solve for x, you get some answer, oh, x equals 8. It's really easy to plug 8 back into the original problem and check that 8 is the right answer. So you get the best case is you have a situation like that, you don't know how to get the answer, but if you have the answer, you can check it. That's a really nice thing. Or if it's just some way for the user to find more information or get a general idea, that's also really great for LLMs. You have to be a little wary, though, if an LLM is giving someone an exact answer, because that exact answer may not be correct. Okay. You can mitigate this through prompting. You can say, hey, if you don't know, say you don't know, and that sometimes works. You can also fine tune, which helps a little bit. We won't go into too much of that, but we will talk about the instruction tuning, which is how ChatGPT was created. The fine-tuning methods are LoRa and QLoRa, where you're not fine-tuning the whole LLM, you're fine-tuning just little pieces of it that get added to the LLM. And so that makes it more doable. But if you have a lot of training data, that's a good thing to do. And you can start here at these links. Now, so privacy is another big issue. Some people were still concerned about sending data around. And so you can use this PHI scraper that I mentioned before, and that's Presidio is a good one. And what it does, if you have something that says Sallyson went to the store and her personal ID number is 1776, Presidio will automatically go in and replace the name Sally Salison with, Aniket Thompson, and replace the ID number with a random number. And so that way it's still semantically more or less the same, as long as you don't care about the exact name, and you can pass it to an LLM, but the person's privacy is preserved. So that's, there's links for that. And then you can use LangChain as a really easy way to use it. And even when I'm not using LangChain, I still use LangChain as the interface to Presidio because it's just such an easy interface. You can run LLMs locally. So the bottleneck is GPU memory. So these LLMs are really big, and you have to have a GPU that fits the parameters of the LLM in memory. You can mitigate this through quantization, which means you take the parameters that are stored in like 32 float and quantize them down into 8-bit floats, and basically you just kind of round them to 8-bit floats and even 4-bit floats. And that works surprisingly well to save memory, and you don't lose that much from it. So here's a good link for that. You can use smaller models such as Mistral, 7 billion parameters, and that's small. So that's what's amazing about this, is that these models are so big that 7 billion floating point numbers is considered a small model. And I found that local models and fine-tuning work better if your domain is niche. But if you need a lot of just general common sense, then the bigger models is probably what you're going to need. And then to find out which model's best, they have a leaderboard on Hugging Face. So this is really nice because people just put in, hey, here's what worked for me, given a bunch of 2 models side by side with their answers. And you see GPT is at the top, GPT-4. The big news a few weeks ago was that Microsoft made it up into the top, the second spot. Or was it Google? I think it was Google, sorry. Google made it up into the second spot. So that's cool. Now, yes. Okay, and then there's a question someone asked about the role of quantization when running the GPU locally. So yeah, quantization allows you to run it locally on a smaller GPU. So you can run, if you quantize, you can run a 7 billion parameter model on your laptop. Or you can quantize like a 60 billion parameter model and then run it on a GPU that's cheaper. And so if you're running your own, then you'll probably want to do quantization. And then another question that came in is, and then, yeah, for the quantization, look at the links I gave you in the term quantization, LLM, and then you'll have to go down the rabbit hole of getting your quantized model. You usually can download them from Hugging Face, and there's this patron saint of quantization called the Bloke, and he's the one who puts quantized models on Hugging Face that you can just download. And then please point out a situation when LLM would be overkill in the context of NLP, e.g., for example, using semantic similarity. Okay, yeah, so you don't need an LLM if you don't need a conversation. So if you're just doing search like we had before of finding the fans or the Michael Jackson song, you don't need an LLM at all. You just need the embedding. And the embedding is pretty simple. In fact, at its simplest, you can just download the Google embedding link I gave you there, or Simple Transformers, and run it locally. You don't need anything in the cloud to do the embeddings. And they work pretty well. So if you're just wanting to do search, you don't need to have a conversation, then that first part of the talk where you're using the semantic search with embeddings is the way to go. And then, and then how do LLMs remember conversational history and memory, or is that a completely independent process? So LLMs do not remember the conversation at all. So you have to pass the whole conversation. If you're continuing a conversation with an LLM, you have to pass the whole conversation to it every time. Now, ChatGPT recently came out with some things behind the scenes where, not in the API, but in the conversation where you have it online, it will remember. But what it's doing is behind the scenes is storing your conversation and then passing it in in the prompt. And so yeah, they don't have memory. And let's see, let's do that. And then quantization, I think I did that. If I accidentally marked your questions answered and didn't answer it, let me know. And then what methods can be employed to mitigate the issue of hallucinations LLM? How effective are they? Yeah, so to mitigate hallucinations, you can make sure you pass in the right information and tell it to use it. And you can tell it to not answer if it doesn't know. And that's about all you can do. It will still hallucinate sometimes. Now, the bigger models, like the GPT-4, they hallucinate less. They're more accurate, but there's nothing you can do to eliminate it completely. Okay. There we go. Cool. All right. So now, one problem with running your LLM locally is that it is really hard to get a GPU. Now, this talk is sponsored by a cloud provider, so maybe they solved that problem. But I've had the problem in the past, at least in the US, of getting a GPU. And there's this old sketch called The Cheese Shop from the 1970s, from this link before. You should link below. You should watch it. It's hilarious. And this guy comes into a cheese shop and there's no cheese. He's like, but this is a cheese shop. And that's the whole joke. There's no cheese at the cheese shop. And when I found that renting GPUs has been a little bit like that. Now, maybe our provider solves that problem. And so then you guys don't have to worry about it. But I found that it really is kind of like that, at least when I was doing this in the US. How about a little A100? And they're like, oh, I'm afraid we're fresh out. Or how about V100? No, only at the first of the week. Or a T4. Oh, the cat's eating it. And so it's been a real challenge. And I've had some luck with serverless GPUs. But if our sponsor here has actual GPUs you can rent, then it's not a problem. So that's great. But then this, as I was making this slide, I did come up with a great example of hallucination, because ChatGPT now will also generate images. And so here's a cheese shop, right? A guy in a cheese shop, he's having a great time, he's handsome, it's a beautiful shop, and it's full of cheese. But I wanted a cheese shop without cheese, right? So I said, okay, how about with no cheese? And then ChatGPT's like, oh yeah, okay, here's a revised picture featuring a man in a cheese shop that has run out of cheese. The image captures the sense of surprise and the empty surroundings. But it looks like there's a lot of cheese there, right? I mean, what's up on the shelves? That looks like cheese to me. And so I said, no. All those round things look like cheese. Can you make me a shop empty of cheese? And it's like, oh, okay. I've created a new image of you depicting a man in a completely empty cheese shop with absolutely no cheese in sight. This illustration captures the emptiness of the man's perplexed reaction. But there's cheese everywhere in the cheese shop, right? There's, behind the counter. Now there's some empty shelves in the back, but there's plenty of cheese in the cheese shop. So I say, those round things are cheese. Please remove the cheese, please. And it says, oh, okay. This time I've created a new image for you where the cheese shop is now completely empty without any cheese objects or objects that might resemble cheese. The scene captures the man's reaction to the stark emptiness of the cheese shop, but there's still cheese, right? And so this is a great example of the kind of hallucination that you'll see, because I'm asking for something that really makes no sense. I'm asking for a cheese shop with no cheese. In fact, since it makes no sense, it's the basis of a famous comedy skit. But a human can understand the concept, a cheese shop with no cheese. But ChatGPT can't, because it doesn't use human understanding of things. It uses statistical correlations between things it's seen in the world, through videos, or I guess this was trained with images and captions, right? And the idea of a cheese shop with no cheese just doesn't make any sense in our everyday experience, even though theoretically it makes sense. And that's why ChatGPT just completely fails on this, or large language models in general would completely fail on this. And it's pretty funny. But it's a hopefully an illustrative example of the kinds of things you just can't get around. But the more common you're talking about, like at the very beginning, we had this example of general relativity, which to humans seems like a really hard concept. Of course it is, but there's a lot of things on the internet about general relativity. So you can have a fluid feeling conversation with it, and it can even help you gain new insights. But ChatGPT isn't really understanding what it's talking about. It's just pulling out correlations. And so that's the next part of the talk, is how this correlations work. And I think we have about 15 minutes left, so that should be good. Okay, so there's 3 technologies that enabled ChatGPT to really pop. So one is language modeling, and 2 is transformers, and 3 is instruction tuning. And so we'll go quickly through each of those, or semi-quickly. So language modeling, this was 2012 or so. This started being how things work. So machine translation used to be really terrible, but then recurrent neural networks made it better. And the way it works is you have some sentence like the patient fell, and you have and you convert the into a vector, and then vector H0. And then you have you have patient, which gets converted into another vector, and then an LLM sitting between these 2 points converts the vector from and the vector from patient into a new vector. And then you have fell has a vector, and that vector, the same LLM converts the vector from representing everything in the sentence so far in H1, and the vector from fell into a new vector, H2. And this process goes to the end until you have like a terminal point, like a period. And now you have H3 that represents, and the LLM sits like, kind of right here in between these 2 things, and grabs the vector from the period and the vector from the sentence, everything so far, and combines them into a new vector. And that vector then represents the patient fell. And the way this is trained is, imagine we have machine translation, and so we're translating this sentence into Spanish. And so you first have it generate a first word, like L. And then from that, you generate a next state vector. From that next state vector, you generate paciente, or patient, which is the word for patient. And then if it generates a word that's not paciente, we know the answer because we have a bunch of English-Spanish translations already, and we know the answer is paciente. So we say, no, the answer is paciente. Update your parameters so that paciente is the most likely. And then you keep doing this, updating the parameters so that the word we know that's most likely is the word that's generated. And that's how this is trained. And so then it can go all the way to the end and say, el paciente se cayó. There's a question about how can NAS technique be leveraged to optimize the architecture of large language models? I'm not familiar with NAS technique. And then asking about text and vision and seamless alignment between cross-lingual and cross-modal. So for cross-lingual and cross-modal, the alignment works really well because there's no, we have cross-lingual, right? It just works in tokens. and it doesn't care what language that token is from. These tokens, paciente and se and el, all kind of correlate together, but through machine translation, they get combined together. So the cross-lingual works really well, and then cross-modal between language and images, you could then have it generate this part of the patient fell could actually be an image, a convolutional neural network that represents an image. And then you start with that vector that's from the convolutional neural network, and then you generate words from it. So that's how you can combine, because here this is just a vector. And once something's in a vector, it could either be an encoding of a word or encoding of a sentence or an encoding of an image, and then you can generate the machine translation. But in that case, the machine translation is not translation, it's the caption of the image. So it's trained with captions. And then I'm not familiar with the NAS technique, so you can possibly just tell me what that is, and I'll see if I can answer that. Okay, now, so we've got this machine translation. Then they found that when you're doing machine translation, if you're here trying to generate say, right, you've got the vector for H4, which is the encoding of L, and the vector from the, the previous word. Instead of looking at just the previous word and the encoding of the sentence so far, what if you looked at that in addition to looking at all of the words of the sentence you're encoding? You could pay attention to all of these things you're trying to encode that were encoded as well, in addition to that decoding so far of the sentence. So instead of just starting from H3, which is the final encoding of the sentence you're encoding, you take all of the stuff so far. And that is, attention is all you need. And that is what led to transformers. So that brings us to our second piece. And someone asked in their question, the NAS is neural architecture search. So neural architecture search is looking at different types of neural networks to generate your answer. So we've looked at, just now, we looked at recurrent neural networks, which is one type of neural network. And then we said we moved to transformers, which is another type of neural network. So neural architecture search would be you generate a bunch of different architectures, and then you try each one out on your problem. You train each architecture, and then you see which architecture works best for your problem. So that has its place. I haven't worked with that a lot, but of course, as you can imagine, this is a lot of computation, because not only do you have to train each neural network, not only do you have to train a neural network, you have to train every generated neural network you generate and then evaluate it. So it's a big computational problem, and if you have a big search space and a lot of computers, you can do some cool stuff. But it's more in the academic realm at this point. But yeah, it's definitely awesome. I mean, that's kind of, you could argue that's what evolution is doing. So very cool. Okay, so now, so that's transformers. So let's go into, in the 7 minutes that remain, how transformers think. So transformers, of course, was taking the RNNs, adding attention, and then throwing away the RNN and just doing attention. Attention is all you need, is the famous name of the paper. And so imagine here we have the patient, question mark, and she. So for each word now, you have a key, query, and value vector. And so the query vector queries the different key vectors around it. So what it does then is it takes the weighted values, the key in the query. So if you have your query, how relevant is this middle token to this tokens around it? Your query matches their key, and you do a dot product, you get a scalar, and that's the weighted value. I'm sorry, that's the weight. And then the weighted value is you multiply that by the weighted value of the vector, and you sum all that, and then you get the vector at the next level. So let's look at that in a little more detail. So recall from matrix multiplication that xmn times yno gives you zmo. And so you've got these sizes, z of a shape, m by o. You've got these sizes, vector size, embedding size. And so you learn these weight matrices. And at each level, but the embedding is only learned once, but you learn these at each level. And then so the first step is you get the embedding matrix, which is L by D. So it's for each word in the thing you're embedding. And then D is like how big your vectors are. So it's L by D. So, if it's 10 words, it's 10 by, and then 1,000, 10 by 1,000 for how long your vectors are. And then you compute your queries, keys, and values by multiplying that matrix by the query matrix, the key matrix, and the value matrix. And you compute your attention weights, which is this, the dot product. And then you use that to compute the vectors at the next level. So what we see on the right-hand side here is the matrix equations for what we saw here. And then, so GPT-3, we don't know what GPT-4 is, but GPT-3 has 96 heads, which is different versions of these, and embedding size of 1248, and in 48 layers. So 48 versions of each of these matrices. And so you can see how it would get the billions of parameters if you have 48 versions of each of these huge matrices. And so before we go on to the final thing that makes this work, let me look again at the question. So neural active research is a cutting edge technique, yeah, within the field of auto machine learning. I mean, yes, I understand, that makes sense. And yep, automated search. So that's right. It's an automated search for different architectures. Yep, that makes sense. I've seen that. There is Kenneth Stanley used to be in my lab. I mean, he didn't work for me. He was in the same lab I was in when I was a student at UT Austin. He's a big name in that area. He is in Florida. And then, very nice. And then someone asked, are the slides recordings going to be shared? So at the very beginning, I typed in the slide location that's on the internet. You should be able to find that as jonathanmugen.com. And I don't know about the recording. And then, oops, that's not. And then someone asked a question: are LLMs imbued with causal reasoning, allowing them to generate counterfactual what-if scenarios, thereby enhancing interpretability? No, they are not. So they don't form a causal model of the world. That's why they have some of these hallucination problems. They don't really understand. They're just looking at statistics. Okay, now let me go back to that. Let me type in where my website is, where the slides will be again. www.jonathanmugen.com. I think it's writing and press. Okay, there we go. Now, all right, now the final part here in these final 3 minutes. I mean, I can stay around a little longer, but I know some people have to go. So instruction tuning. This is the thing that really made LLMs pop and made ChatGPT kind of the thing that it is. So you first train an evaluation model to determine how good the output is. So you have humans rate a bunch of outputs and determine, okay, well, this output was better than this one. And so this is pretty human intensive to train a model of this additional model to determine how good the LLM outputs are. And then once you have that, you can train it with reinforcement learning. So you train an evaluation model You're training a separate model that provides a reward or how good that first model is. And then you use that critique model to update the generation model autonomously. And it just kind of self-trains. And so the way that works through that self-training process is reinforcement learning, which goes back 100 years or so from training of animals, became behaviorism and psychology, and became artificial intelligence. And basically reinforcement learning is you kind of wander around in search space till you do something good, and then you remember the path that got you there. And you say, being close to being good is great, and being kind of close to being kind of good is kind of great, all the way back. And then you learn a policy that represents what you should do for every state, and that gets you to the pot of gold. And so that is the second piece, and that is the second piece of the third piece of how ChatGPT works behind the scenes. And that is our talk. We did flexible document search, which is going to be helpful right out of the gate if you need, vectors looking for Michael Jackson songs or sports fans. And then you can question answer, bring the LLM in, large language model. You can do exact calculations. Keep in mind that there are hallucinations, as we saw with the cheese shop with no cheese. And now you know how at the level of matrix multiplication, how LLMs work. And that is my talk, and I'll answer any other questions. There is one question here. What is your favorite use case of LLMs, and which industry do you think is benefiting the most? So my favorite use case for me is just learning about new things. So every time I don't understand something and a Google search or Bing search or web search isn't enough, then I have a conversation with the LLM. And then which industry is benefiting? It seems like all industries, it doesn't seem to be an industry-specific kind of thing, but you use a large language model when you can't compute an exact answer. So if you know how to compute an exact answer, you just do that, like we've always been doing, just code it up. But LLMs are really useful when we have the squishy part of our world, such as language or images, to try to understand what's happening. Now, we've seen that understanding isn't exact because the LLMs don't learn about the world the way humans do. Humans learn about the world by building causal models, as someone else answered, or someone else asked. But LLMs just work by statistical correlation. So there's some things they can't do. And then someone else asked, how does the attention mechanism combine keys, queries, and values and compute weighted representations, and what mathematical operations underpin this process? Okay, so the keys, queries, and values is a matrix. So you multiply a learned matrix by the embedding value. And that values for that matrix are learned by gradient descent, which is just a standard neural network training mechanism. And then explain the significance of scaling the dot product of queries and the keys by the square root of the dimensionality of the key vectors. How does this affect the attention score? Yeah, I vaguely remember looking at that at one point, but I don't really remember the answer, so I'm sorry I can't answer that one. And then in transformer architectures, how do positional encodings injected in the input provide information about token positions? Are there challenges when handling long sequences? So there are challenges when handling long sequences because it scales in n squared. So it has, every token has to look at every other token. So as you get long sequences, you have a blow up in scaling. And so there are certain methods about working on that, architecture improvements. And then positional encodings, what they do for positional encoding is they put a sine wave in there. And so you add into the embeddings a sine wave or a bunch of sine waves. that enable you to encode position. So you have one sine wave, a big one, and then a medium-sized one, and then a little one. And then, of course, if you put that together through Fourier transform and all that kind of stuff, you can get something exact out of it. And that's kind of what's happening with the positional encoding. And then the intricacies of multi-head attention to capture different aspects of the input sequence. That's right. So you could have multi-head attention. So one head of attention might be looking for grammar. Another head of attention might be looking for tense, past tense, future tense. Another head of attention might be looking for semantics. And we don't specify what these heads do. We just give it a bunch of heads, attention heads, and have it learn, and it kind of works itself out. Self-attention and cross-attention. Yeah, so self-attention is looking at the things in your sentence to better understand what your sentence is. And then cross-attention would be kind of like in machine translation, where you're looking at the sentence you're translating from to better understand what you should do. And I think, yeah, that one's basically it. How do they differ in terms of input and output? The representations are the same. It's just where you're looking, as far as I understand. And cool. Great. I guess that's it.
Great. Thank you so much, Jonathan, for this insightful session. And a big round of applause for all of you who joined today and participated so actively. But before you leave, we're eager to hear your feedback on today's session. So please take a moment to fill out a quick NPS survey. Your responses are incredibly valuable to us, and they'll help us improve our future webinars. I'm running the survey now. Please fill it. Yeah. So while you fill the poll, I'll just give you an introduction to what we do at E2E Networks. E2E Networks is the leading AI-first hyperscaler from India, focusing on providing advanced cloud GPU infrastructure. We lead the industry as a prominent cloud GPU provider, offering a comprehensive range of NVIDIA GPUs, including the HGX H100, A100, L40S, L4, A40, V100, and T4s. To know more about us, you can check out our website, e2enetworks.com, or if you want to get your hands on one of our GPUs, you can sign up at myaccount.e2enetworks.com.